Hi guys, today I'm doing a presentation on waves. Yay! Okay, so you might be thinking, well, what's a wave? Well, a wave is a traveling disturbance that moves energy in a rhythmic pattern through matter or space. Now, this is what I would call a dictionary definition. That means basically it's super confusing and nobody understands it unless you are like the next Albert Einstein. That is why I will give you some examples. Example number one. Water waves. So water waves move energy through water. Pretty explanatory. It's pretty self-explanatory. But here's a nice little picture that I kind of screwed up on. And here are an example if you don't like my picture. Example number two is earthquakes. Earthquakes move energy through powerful waves from a fault line to Earth's crust. Here's what the fault line looks like in case you haven't seen one. And here is some fault lines from all around the world. Some types of mediums, some types of waves, including water waves and earthquakes, have to travel through a medium. So, what is a medium? A medium is material that a wave moves energy through. They can be solid, liquid, gas, or a combination. However, not all waves require a medium. Take mechanical waves and electromagnetic waves, for example. One does require a medium while the other does not. Mechanical waves do need a medium, so they're like the water waves and earthquake waves that I told you about before. While that means electromagnetic waves do not need a medium. Examples of this are light waves and radio waves. So, electromagnetic waves, that's kind of a strange name, so why is it called that way? Anyway, they have electric and magnetic parts both travel perpendicular to each other along the distance the wave is traveling. Here's a little picture, and as you can see, the electric parts are traveling vertical to the direction the wave is traveling, while the magnetic parts are traveling horizontal. So, two types of waves are transverse and compressional waves. Transverse waves cause particles in matter to move back and forth at right angles to the direction that the wave travels. Compressional waves cause particles of matter to move back and forth along the same direction in which the wave travels. So parts of a transverse wave. The crest is the high point, while trough is the low point. And parts of a compressional wave. Compression is the place where the wave is coiled together, while rarefaction is the part where the wave is spread apart. Here's two nice little pictures, and this one's a transverse wave, this is a compressional wave, and for the transverse wave, right here, here, and here would be the crest, while down here, you can't really see it, and down here and here would be the trough. For compressional waves, the compression would be right here, and it's even labeled and everything, while the rarefaction would be right here. So, wavelength. Wavelengths is the distance between one point in a wave and the nearest point moving with the same speed and direction. Here's a nice little picture, and right from for a transverse wave from crest to crest or trough to trough would be one wavelength. Frequency. Frequency is the number of wavelengths that pass a point each second. So they're measured in hertz, that's the abbreviation Hz, and 1 hertz equals 1 wavelength per second. 1 wave per second. Velocity is how fast the wave travels. It's also known as wave speed. And the faster the wave travels, the more crests or compressions pass each second. And it also depends on what type of medium the wave travels through. So it'll be a little bit different if the same wave travels through rock than it would be if it traveled through just regular air. So this is where it gets kind of mathy. And there's actually an equation for you to figure out velocity. And the equation is v equals lambda times f. Lambda is this little symbol over here that looks kind of strange. V stands for velocity. The weird symbol lambda stands for wavelength, and f stands for frequency. So here's like a little problem for you to kind of test out your skills with it. And a string moves up and down in a transverse wave. The string's wavelength is 7 millimeters and its frequency is 1.3 hertz. What is the string's velocity? So here's your formula again, V equals lambda times F. And you just plug in the numbers, so 7 millimeters for wavelength and 1.3 for frequency. And you just multiply it out to get 9.1 millimeters per second for velocity. So you can also use it to solve, you can also use the equation to solve for wavelength or frequency. An earthquake is moving at 4,900 meters per second and has a wavelength of about 400. What is its frequency? So here's your normal equation, and since we're solving for frequency in this particular problem, you just have to get frequency by itself. So you divide lambda by itself to cancel out, and what you have to do to one side, you do to another. So you would divide V by lambda. So your equation would now be V over lambda equals F. And you just plug in the numbers, so 4,900 for velocity and 400 for wavelength. And you just divide it out, and you get 12.25 hertz equals frequency. If you want to solve for lambda, or also known as wavelength, your formula would be V over F equals lambda. So that's all, folks. I hope you learned something about waves and wavelengths and everything like that. And here's my bibliography for all those pictures I used. And thanks for watching.